Water covers 71% of our planet. But did you know we can harness its raw, surging power to generate limitless electricity? This isn't just a dam, it's a colossal energy engine.
Today, we're dissecting the ingenious, tech-savvy process, how simple H2O is transformed into the electric current powering your life. Get ready to dive deep into hydropower dynamics.
The core concept relies on gravity and potential energy. We elevate water to store enormous energy, waiting for its release.
When water is dropped, potential energy converts into kinetic energy, the energy of motion. This is the fundamental driver of all hydro systems. Hydropower is clean, meaning it doesn't burn fossil fuels. It merely utilizes the natural water cycle, making it inherently sustainable. Historically, water wheels paved the way. Modern turbines are simply highly optimized, hyper-efficient descendants of that ancient technology. Gravity provides the head, or the vertical distance the water travels. Higher head means more pressure and greater energy yield. We measure this power in megawatts. A large plant can generate thousands of megawatts, capable of powering millions of homes.
Conventional facilities, often centered around massive dams, are the most recognizable form of hydropower. They control vast water bodies. The reservoir acts like a massive battery, storing water and regulating flow to meet fluctuating energy demand throughout the day. The intake structure is the gatekeeper. It screens the water, removing debris like logs or trash before it enters the system. Precision engineering ensures only clean water moves forward, protecting the sensitive, high-speed machinery inside the plant.
Next comes the penstock, a massive, pressurized pipe designed to channel the water swiftly and safely from the reservoir to the turbine. The penstock must withstand immense hydrostatic pressure, which is why material science plays a critical role in its construction. At the end of the penstock, the water's potential energy is now pure kinetic energy, ready to strike the turbine blades.
The turbine is the heart of the operation. There are several types, depending on the head and flow rate available.
For high-head setups, like those using huge dams, the Pelton wheel uses high-velocity jet streams hitting specific buckets.
For lower-head systems with high flow, Francis turbines are common. They use pressure differences and radial flow to maximize efficiency. Water pressure forces the turbine blades to rotate with incredible speed and force, converting linear motion into rotational energy. This rotational energy is transferred via a shaft directly to the generator, usually located right above the turbine pit. The generator is where the magic happens, electromagnetic induction. It uses a series of magnets and copper coils. As the massive rotor spins, it creates a moving magnetic field, inducing current flow in the stator coils. That's electricity. After exiting the turbine, the spent water flows out through the draft tube and returns to the river, completing its cycle downstream. The key takeaway is efficiency. Modern hydro systems can achieve efficiencies exceeding 90%, minimizing energy waste. Not all hydro plants only generate electricity. Pumped storage facilities act as giant energy storage systems, essential for grid stability. They feature two reservoirs, an upper and a lower one. The process uses electricity generated elsewhere to pump water uphill. This pumping occurs during periods of low energy demand, such as late at night, when electricity is cheap and abundant. Effectively, the upper reservoir stores energy, much like charging a massive lithium-ion battery, but using water and gravity. When energy demand spikes, typically in the morning or evening, the stored water is released to generate instant power.
This is critical for balancing intermittent sources like solar and wind, providing power instantly when the sun sets or the wind stops.
Pumped storage uses reversible turbine units, often Francis turbines, designed to operate efficiently in both pumping and generating modes. Switching modes can be accomplished rapidly, allowing the plant to respond to grid emergencies within seconds. These systems are vital for grid frequency regulation, ensuring the balance between power supply and consumption remains precise.
Building these dual-function plants requires extensive civil engineering, often involving subterranean powerhouses and tunnels.
The overall energy return efficiency for pumped hydro averages around 70 to 85%, making it one of the most effective grid batteries available. While conventional hydro plants focus on continuous generation, pumped storage emphasizes flexibility and reliability.
This technology is not new, but its role is becoming exponentially more important as we integrate more renewable sources onto the grid. It ensures that renewable energy is always accessible, even when the primary generating conditions are not optimal. Not every hydro solution requires a giant dam. Run-of-river projects utilize natural stream flow with minimal water storage. They divert a portion of the river flow through a channel or pipe, drive a turbine, and then immediately return the water downstream. Since they require little or no reservoir, their environmental footprint is significantly smaller compared to conventional dams. However, their energy output is dependent on the seasonal flow of the river, meaning they are less reliable during dry seasons. The intake must be carefully designed to allow fish passage and minimize impact on aquatic ecosystems, often requiring fish ladders. Run-of-river plants are often ideal for remote communities or smaller decentralized power grids, offering localized energy independence. These systems prove that massive infrastructure isn't always necessary. Sustainable energy can be captured on a much smaller scale. Taking hydropower further, we tap into the planet's largest water bodies, the oceans. Tidal and wave energy are predictable and powerful. Tidal power, the gravitational pull of the moon, creates reliable twice-daily surges we can harness using barrages or stream turbines. Tidal barrages are essentially dams built across estuaries, creating a controlled difference in water level that drives turbines. Tidal stream generators operate like underwater wind turbines, capturing kinetic energy from fast-moving currents in narrow channels. Wave energy converts the vertical motion of ocean waves, the bobbing up and down, into mechanical energy. Devices like oscillating water columns utilize hydraulic systems to pressurize fluid and drive a generator onshore or offshore. Ocean energy faces unique challenges: corrosion from saltwater, extreme weather, and the sheer force of massive waves. Despite the engineering hurdles, the potential energy available in global tides and waves is astronomical, representing a massive future resource. These technologies represent the next frontier in hydrogeneration, pushing the boundaries of what water power can achieve. The future of hydro involves miniaturization and smarter integration. Small hydro systems are growing rapidly worldwide. Micro-hydro setups can generate anywhere from 5 to 100 kilowatts, providing essential power in areas far from existing infrastructure. We are also seeing innovations in hydrokinetic energy, harnessing the flow of rivers without dams or diversions. Floating solar panels on hydro reservoirs offer a synergistic solution, optimizing land use and reducing evaporation losses. Environmental mitigation techniques are constantly improving, focusing on minimizing habitat disruption and sediment flow issues. Smart power plant management uses AI and real-time data to predict water inflow, optimize turbine scheduling, and maximize power output. This precision ensures that water resources are managed sustainably, balancing power generation with ecosystem needs. The challenge remains aging infrastructure. Many conventional dams were built decades ago and require significant modernization and upgrades. Modernizing turbines and generators can drastically increase efficiency, often boosting power output by 10 to 30% without structural change. Advanced materials like polymer coatings and specialized alloys enhance turbine lifespan and reduce maintenance costs dramatically. Hydropower will serve as the reliable backbone for a renewable grid, providing the essential storage and quick response needed for the transition. Once generated, the raw electrical current is stepped up dramatically by transformers before it leaves the plant. Why step up the voltage? Higher voltage minimizes energy loss when transmitting power over long distances across the grid. The power then travels through high-voltage transmission lines, often spanning hundreds of miles, connecting the plant to substations. Substations act as regional traffic controllers, lowering the voltage in controlled stages for local distribution. Distribution lines carry the final usable voltage directly to your local neighborhood transformers. Ultimately, water power is delivered instantaneously to your home, powering everything from your lights to your smart devices. Maintaining the grid stability requires constant coordination between hydro generators and other power sources, a complex digital dance. The sheer scale of coordination needed to ensure 24/7 reliability demonstrates the sophisticated engineering behind modern energy.
Hydroelectricity is proven, reliable, and crucial. It represents humanity's success in harnessing natural forces for civilization's needs.
From the reservoir's immense pressure to the flick of your light switch, the water's journey is complete, ready to begin again tomorrow.
We hope you enjoyed this deep dive into water power. Don't forget to like and subscribe for more updates on cutting-edge energy technology.